This is the third part of the presentation in which I'm talking about maximum flow problems. In this part, I'm going to talk about how we can use the ford-fulkerson method to solve the examples. We have seen in the previous part that this method consists of, first, we should know whether an arc has a property of increase or reduce, or both. And then second, we try to label the nodes using forward or backward arcs. And finally, we try to increase the total flow. Later in this part of this video, I will also talk about how we can know if the solution that we get is already optimal. Let's solve example 3. So we always start by doing nothing to the network. It means that we set the flow through each arc equals 0. Nothing flows through this network. Because the flow equals 0 on all arcs, it means that the property of all arcs in this network is still increased and only increased. Because the flow is still 0, we have the capacity. For example, this capacity is 2 and our current flow is 0. So of course the property of the arc is increased and only increased. Now we can try to label this network starting from the source node. We can go to the node 1. This is a forward arc. And then we go to node 2, also a forward arc. And then we go to the sink, which is also a forward arc. Because all arcs that we have labeled are forward arcs only. So we have case 1, and then we take the minimum of the possible increases along this chain. So here it is possible to increase by 2, it's possible to increase by 3, it is possible to increase by 2 at this arc. We take the minimum of 2, 3, and 2, the minimum is 2, so we are going to increase all arcs in this chain by 2. And we'll see the result, for example, from source to 1, we will have the flow of 2 in the next slide. So now you can see that previously we have 0 flow through the network, like from source to 1. Now we have the flow of 2 going from source to 1. So the value inside the parentheses are the number of flows that is flowing from one node to the other. Now let's just repeat the same procedure. You try to find out what are the possible properties for each arc. So it can be increased only, it can be reduced only, it can be both increase and reduce. Okay, so this is an important thing to keep in your mind, that an arc can have both increase and reduce properties. Now let's try to label this network and try to reach the sink. We start from the source. We cannot go to 1 because this arc source to 1 is a reduced arc, and we cannot use a reduced arc to move forward. So if we want to move forward, we need to use this arc. That's how we label 2. And then 2 to sink, we cannot use that arc because it's a reduced arc. We cannot go forward. But you can see that we can go backward if we use this arc, because it has a property of reduce, so we can go backward. That's how we label node 1. And then from node 1 is quite straightforward. We just move forward using the increase arc, and then we move forward again because 3 to sink is again an increase arc. We have a mix of forward and backward arcs, so this is case 2. So for case 2, we separate for the forward arcs and then the backward arc. For the forward arc, we find K1, which is the minimum increase. So from source to 2, we can increase by 3. From 1 to 3, we can increase by 4 at most. And then from 3 to sink, we can increase by 1. Take the minimum, so minimum is 1 for K1. K2 is talking about just the backward arc, and we see that for this backward arc, we can reduce at most 2 units of flow. So K2 equals 2. We take the minimum between K1 and K2, and the result is 1. Which means that for every forward arc in yellow, we will increase by 1. And then we will reduce the backward arc by 1. This is the result. For example, you see that from source to 2, now the original flow is 0. It becomes 1 on the figure on the right. And then from 1 to 2, originally the flow is 2, but now it becomes only 1 because we reduce the flow from 1 to 2. Okay, do the same thing again. Find the properties of each arc and then try to label the sink if possible. We start from the source. We can go to 2, that is a forward arc because it has an increased property, so we can go forward. And then we can go backward to 1 because it has a reduced property, so we can go backward. We can go forward again using this increased arc, but now we are stuck. From 3, you cannot reach the sink because the property from 3 to sink is a reduced arc. You cannot go forward. So if this happens, it means we have reached the optimal solution. And then for this case, the optimal solution is having the maximum flow of 3 from source to sink. This is 1 and this is 2, so the total flow is 3. Here is another example. So again, we always start by doing nothing to this network, so no flows from any node to any node. So all arcs have flow equals 0. If all arcs have 0 flow, it means that all arcs have the increased property, which means that we can just simply start labeling because all arcs are increased. So we can just go forward, let's say from source to 3, 3 to sink. Of course, you can go forward, let's say from source to 1, 1 to sink. That is also okay to do that, but I'm just following the example that is shown on your textbook, so you won't get confused. Okay, so this is a forward arc, this is a forward arc, so we have case 1, and then we take the minimum between the possibility to increase by 3 and the possibility to increase by 5. The minimum is 3, so we will increase all these forward arcs by 3. Now you can see on the right, the figure shows that we have increased from source to 3 by 3, and then from 3 to sink by 3 as well. So repeat the procedure. Start by labeling each arc by its properties. It will help us to decide whether we can do a forward arc or do a backward arc. We try to label this network again. We start from the source, and then we use this increased arc to have a forward arc. And then we go down because it's an increased arc, so it's possible. And then we go down again to label node 3 using this increased arc. Finally, we reach the sink by moving forward again using this increased arc from 3 to sink. Because all arcs are just forward arcs, again, we only have the case 1. So take the minimum of the possibility of increasing the flow. Possibility here is 2, this is 7, 2, and this is 2. Okay, this is 2 because you already have the flow of 3 units, and then the capacity is 5. So the possibility to increase this arc is only 2. Now the k means that you take the minimum of all those possibilities to increase all arcs in your chain. And then the minimum is 2, so we will increase all of these arcs by 2. And we will see the result on the next slide. So here is the result, for example, from source to 1. Now it has flow of 2 units. We do the same thing again by labeling each arc with its properties. Again, you should notice that an arc may have both increase and reduce properties. I keep on emphasizing this thing because usually this is kind of a misconception among the students, which they think that an arc can only have increase or reduce property, which is not true. An arc can have both properties. So again, try to label the sink if possible. We start from the source. Now we move on to node 2. This is a forward arc. And then now we cannot go from 2 to 3 because it's a reduced arc. We cannot go forward using a reduced arc, but we can go backward using the reduced arc from 1 to 2. So this is a reduced arc, and then we can label 1. From 1 to sink, the move is forward again because the arc has the property of increase. Now we have case 2 because source to 2 is increased, 1 to sink is increased, but 1 to 2 is a reduced or backward arc. So separate, this is case 2, and then we take the cases separately. So for K1, we find out the minimum of possibility to increase. In this part, you can increase by 8. In this part, you can increase by 2, so the minimum is 2. For the backward arc, we have only one backward arc, and then here in this backward arc, you can reduce at most 2 units. So, so this is 2, so K2 equals 2, which means that along the backward arc, you can reduce at most 2. Then you find out the minimum between K1 and K2. The minimum between 2 and 2 is still 2. So we will increase the forward arc by 2, and we will reduce the backward arc by 2. Here is the result. You can see that from 1 to 2, it has been reduced from 2 units of flow to become 0 unit of flow. Now repeat the same thing. We label each arc by its properties, and then we try again to label the sink if possible. Start from the source. We can move forward using this increased arc. And then now we're stuck. You cannot go from 2 to 3 because it's a reduced arc. You cannot go forward. You cannot go backward from 2 to 1 as well, because now 1 to 2 is an increased arc. So now we have obtained the optimal solution with the maximum flow of 7. 2 from here, 5 from there. So the total maximum flow is 7 for this case. So anytime you cannot reach the sink anymore, you cannot label the sink, it means that you have got the optimal solution. So that's how the ford-fulkerson method works. Now let's talk about this thing. How do we know if the solution is optimal? We will see the concept of cut, and then there is the small cut and the big cut. The big cut means that everything is written in capital letters, C-U-T. All letters are in capital. So we have a small cut, we have the big cut. So let's say we have a set of nodes that contains the sink, but not the source. And then suppose we call this set of nodes as V prime. Okay, so this V prime must contain the sink, but this must not contain the source. And the cut, the small cut, is the set of all arcs ij with I not in V prime, but j is in V prime. Okay, so j is the one of the nodes that we selected to be inside the set of V prime. Now the capacity of this small cut is the sum of capacities of all arcs in the cut. So we will take the summation of all capacity of the arcs that is included in the small cuts. How can we interpret cut physically? A cut is a set of arcs in which if we remove those arcs from our network, it will be impossible to travel from the source to the sink. So now you can see the logic behind why it is named as a cut, because if we remove these arcs, now your network is cut. There is no way to reach the sink. Okay, so that's how the cut is got the names. And then a network may have many cuts. So it's not only one possible set of cuts that can cut out the network, but we can have a lot of possible cuts. We will see the examples in the next slide to make these ideas clear. Now let's take a look at examples of the cut. So suppose I chose nodes 1 and sink to be in V prime. Remember that the requirements of nodes in V prime is that you need to include the sink, but you cannot include the source. So any other node is okay. So here 1 and sink is okay to be included in V prime. So the cut is the set of arcs ij in which j is in V prime, but the I is not. So you can see 1 is in V prime, sink is also in V prime. So these arcs defines the cut for the selection of nodes in V prime. The capacity of the cut is 3 because from source to 1 you have the capacity of 2, and then from 2 to sink you have the capacity of 1. So 2 plus 1 equals 3. And then physically you can see that if we remove those arcs, there is no way that you can travel from source to sink. So I'm taking this arc out. I'm also taking this arc out. And now you cannot travel from source to sink. Let's say I chose 1, 2, and sink to be in V prime. This is also okay because V prime contains sink, but does not contain the source. So what are the arcs in the cut? So we have only source to 1 and source to 2. Because remember, you need to find the arc such that the arc ij, j is in V prime, but I is not. So these are the arcs, and the capacity of this cut is 10. Again, we can see that if we take those arcs out from our network, there is no way to travel from source to sink. Now let's say again if I chose the sink only in V prime. Now it becomes obvious that nothing can travel from source to sink because I'm going to take out this arc and that arc. Okay, so now it is obvious that this cut really cuts the network because you're taking out all the arcs that are leading to the sink. Now, based on the idea of cut, this is the first lemma. It says that the flow from source to sink for any feasible flow must be less than or equal to capacity of any cut. So you may have a lot of cuts, but then this lemma says that any feasible flow the value of any feasible flow must be less than any cut that you have. So the result of this lemma will be useful later, which is to prove that if we cannot label the sink, then we must have obtained the optimal solution. So this lemma will be used next to prove that lemma. So this is the first lemma. It says that if we have an arbitrary cut that is specified by a set of node V prime, which like before always contain the sink but does not contain the source. And then if we perform the sum of the flow balance equation, so what is going out of the node minus going into the node, for all the nodes in V, so V is not the one that we have chosen. So if we sum all the flow balance equations for the nodes that we have not chosen to be in the V prime, we find that this thing here holds. So the first term means that if we check the flow from all arcs in which that I is not in V prime but J is in V prime, minus all the flows that going from the nodes that in V prime to the nodes that are not in V prime, it will be equal to the current flow in our network. Current flow means that the current amount of flow that can go from source to sink in our feasible solution. Now, if you see this equation, the first part actually is the capacity of the cut, right? Because remember, capacity of cut means that we are summing the capacity of all arcs that are going into the nodes in V prime. So the first part here is actually the capacity of the cut. The capacity of the cut minus something, so xij is the flow from node I to j, and then because this value cannot be negative, so then xij minus something positive equals the flow. It means that the flow at any time cannot be larger than the capacity of the cut, right? Because the capacity of the cut minus something positive equals the flow. So there's no way that the flow can be greater than the capacity of the cut. Now I'm just interested about that equality sign. I mean, how would you know that the capacity of the cut minus something will be exactly equal to the flow from the source to the sink? Like here in this example, for example, the current flow from source to sink equals 2. Because so there's 2 units of flow going in from there. So how can we know that? Well, so I'm thinking that let's start by choosing the sink as the only node in the V prime, and all the other nodes that are not in V prime. It means that we cut everything that goes to sink. We cut the network. However, next that because everything, all nodes here must satisfy the conservation of flow constraint. So let's try to catch the flow that cannot go to the sink with a bucket here. So I put a bucket between tree, 2, and sink, which the arcs have been cut. So I put a node and let's check how much flow can we get in that cut. So the lemma 1 says that we need to calculate the conservation of flow constraint for all nodes in V. Okay, so let's do it. So this is the conservation of flow for the source. Going out from the source is source to 1 and source to 2. And going into the source is from sink to source. It must equal 0, right? And then for node 1, going out is 1 to 2, and then 1 to 3, and then going into 1 is from source to 1. This is for node 2. Going out is 2 to sink, which has been cut away, and then going in is from source to 2, and then from 1 to 2. Finally, for node 3, going out from node 3 is 3 to sink, which has been cut away. Sorry, going out from 3 is 3 to sink, and then going into 3 is from 1 to 3. And then we take the sum of all these equations. We can see that some terms will cancel out. Source to 1, source to 2, 1 to 2, and 1 to 3. So the remaining terms is this, minus x from sink to source, plus x2 to sink, plus x3 to sink. And then if you recall that the sink to source, this is just an artificial arc. And this artificial arc equals the total flow, right? Because whatever is going into the sink will go out from this artificial arc. So now we can change this x sink to source with another notation f, which means the flow of the network. Why? Because remember, whatever is going in will be transported out from this using this artificial arc. So this is our current flow, and then if I just move it to the other side, we have this equation, which is this. So the capacity of arc is from 2 to sink plus 3 to sink. This is the capacity of the cut, sorry, not the capacity of arc, but the capacity of the cut, minus 0 equals the flow. And that makes sense actually here if you look at this part. If we cut away the arc from 3 to sink and then 2 to sink, of course the flow that we can contain in this bucket equals to the current flow from source to sink. Because they cannot flow to the sink, we capture it in the bucket, so we catch the flow equals 2 in this case. So that's how I guess the explanation of why the capacity of cut minus something will be equal the current flow. Now another comment is that here the something equals 0 because the only node in the V prime is sink. If we have another node in the V prime, that will correspond to the term in the conservation of flow in the other node. Now the lemma 2 says that if the sink cannot be labeled, then the capacity of the big cut must be equal to the current flow from source to sink. Notice that this is the big cut. It's different with the small cut. So if the sink cannot be labeled, then this is the case. And then this lemma is useful to prove that if we can't label the sink, it means the current solution is optimal. So in ford-fulkerson method, we stop when we cannot label the sink. So in this case, when you have tried to label the nodes, but you cannot reach the sink, and then the nodes that still cannot be labeled, you name it as V prime. And then the nodes that can be labeled so far, you name it as the V set of nodes. Now let's consider an arc ij such that I in V labeled and j is in V prime unlabeled. This is the case. You can label I, but you cannot find any way to label j. Which means that if you can label I, but you cannot label j, it means that you cannot go forward. You cannot go forward. What makes you can't go forward? It's because the flow on the arc is already full, right? If the flow in the arc is already full, the only option or the only property of this arc is reduced. So that's why you cannot go forward, because the flow is already full. Okay, so everything in the side of this equation shows that Xij is really already full. It's already equal to the capacity of the arc. Now let's see another possibilities. Arc ij, in which I is in V prime, so I is unlabeled, J is in V. So I is unlabeled, but J is labeled. Now here, why you cannot label I? Why you cannot label I in this case? Well, because if you want to label I, it means that this arc should have the possibility to be reduced, right? Such that you can go backward. But in this case, you cannot do that. Why you can't do that? Well, the only reason is because the Xij here is already 0. So you cannot reduce this arc any further. So these two cases makes you unable to label the sink, right? Because no way to move forward and no way to move backward. So you cannot label the sink. And then so based on this knowledge, this part equals 0. So now you know that when you cannot label the sink, it means that the current flow is already the same with the sum of all cut in the network. Because the flow cannot be higher than the sum of capacity of any cut, and then you cannot improve your flow anymore, either using increase or reduce. So there's no way to improve the flow anymore, but you have also reached the same amount with the capacity of the cut. It means that your solution has been optimal. And these set of unlabeled nodes V prime that define this cut is the set of unlabeled nodes, and the cut is called the big cut. So big cut is the result from the set of unlabeled nodes at the end of your ford-fulkerson method, when you cannot reach the sink anymore. Now let's apply the lemma 2 into an example. So here, when you try to label this network, let's say we start with the source, and then you can go forward to 2, you can go backward to 1, you can go forward to 3, but now you're stuck. There's no way to label the sink. So in this case, the unlabeled node becomes V prime sink. The other nodes that we can label becomes V. So the cut here is 3 to sink and 2 to sink. This is the big cut. The capacity of the big cut is 3 and the current flow is 3, so this is optimal. So let me repeat, how can you obtain the big cut? So you need to try to label the nodes until you cannot reach the sink. So there's no possible way to label the sink. So that's how you know that you have already got the optimal solution. And then you take whatever is unlabeled into V prime and take whatever is labeled into V. So you might ask, is it possible that the V prime contains sink and another node or some other nodes? The answer is yes. It is just the case in this example, we only have the sink in the V prime. But in another example, yes, it is possible. You just need to remember that V prime contains the unlabeled set of nodes. Okay, the unlabeled set of nodes after you try your best to label the sink in the ford-fulkerson method. So this is the end of the maximum flow problems topic. It's pretty long, right? I don't think it takes this long if I really explain this thing in class, because I can use the whiteboard, I can use different colors of markers, I can just erase the labels and then write down the new labels and so on. And I also think because I try to be as clear as possible when explaining this online, because I cannot assess how far you understand or how far you don't understand something. Anyway, next we are going to talk about minimum cost network flow problems, and this topic corresponds to section 8.5 on your textbook. So I think maximum flow problem is the section 8.3, so we're going to skip one section and just going to the 8.5 section. So see you in the next video, and thank you.